All right, welcome back. This is the end of week 2 in CS50, and this is an excessive amount of what's called ASCII art. People who have spent way too much of their free time actually sketching out most of the scenes from Star Wars entirely in their own ASCII character code. So this is a bit of an animation that's a bit of an internet meme these days and goes around, but we've linked to it on the course's website if you'd like to watch the whole film later. We thought we'd begin, though, not just with ASCII art, but with something a little sexier than that, that paints the picture for this week's and next week's problem domain, that of cryptography and security more generally. Some of you might have seen this actual film before, one of my favorite excerpts of which is this one, that one too, is this one here.
What's going on? What are you doing to my daughter?
Permit me to introduce the brilliant young plastic surgeon, Dr. Philip Schlotkin, the greatest nose job man in the entire universe and Beverly Hills.
Your Highness.
Nose job? I don't understand. She's already had a nose job. It was a sweet 16 present.
No, it's not what you think. It's much, much worse. If you do not give me the combination to the air shield, Dr. Schlotkin will give your daughter back her old nose.
No! Where did you get that?
All right, I'll tell.
No, Daddy, no, you mustn't.
You're right, my dear. I'll miss your new nose, but I will not tell him the combination no matter what.
Very well. Dr. Schlotkin, do your worst.
My pleasure.
No! Wait! I'll tell.
I knew it would work. All right, give it to me.
The combination is 1, 2, 3, 4,
5. So the combination is 1, 2, 3, 4, 5.
That's the stupidest combination I ever heard in my life. That's the kind of thing an idiot would have on his luggage. Thank you, Your Highness. What did you do? I turned off the wall. No, you didn't. You turned off the whole movie. I must have pressed the wrong button. Well, put it back on. Put the movie back on. Yes, sir.
Let's go, Arnold. Come, Gretchen. Of course, you know I'll still have to bill you for this.
Well, did it work? Where's the key?
It worked, sir. We have the combination.
Great. Now we can take every last breath of fresh air from planet Druidia. What's the combination?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
Yes.
That's amazing. I've got the same combination on my luggage. Prepare Spaceball 1 for immediate departure.
Yes, sir.
And change the combination on my luggage.
So if you'd like more of that, that is a classic called Spaceballs. And we have another little classic for you in a little bit. So you might laugh, but odds are, statistically, some of you in this room has a password that's not all that dissimilar from 1, 2, 3, 4, 5. And some of you might even have Post-it notes back on your desk. So 1, 2, 3, 4, 5 is clearly insecure as a password. One, because it's just so easy to guess. Even you, if you're trying to break into someone's account, you might try simple things like that, or the ever-popular password, or something similar. But in reality, what systems typically do, even if a password is weak like that, they're actually store, computer systems, things like this. So if you've ever forgotten a password on a website or one of Harvard's passwords, and you're told by some IT person that they cannot, in fact, tell you your password, but you can change it, that's generally algorithmically correct. For security purposes, passwords are typically not stored in computers in so-called clear text, but rather in ciphertext, in some kind of encrypted fashion that looks mostly like random nonsense. But the reality is that that is the result of applying some mathematical formulas to the original password, 1, 2, 3, 4, 5, the output of which is something crazier looking. The idea being, if you see the crazy looking thing, it's not all that easy, if at all possible, to figure out what the original password actually was. So in short, when you create an account on some new website, Facebook, Google, any of these sites, they're storing in a database your username, and that's generally in the clear, or your email address, but then your password is encrypted. But this seems to beg a question. The next time you log in, time number 2 or 3, how in the world does Google or Facebook or Harvard know that you've typed in the right username and password if they too no longer know what your password is? It seems like once you've encrypted the password, you're kind of screwed because you no longer remember what the new one is if this is all you're storing. So what could you do? What are some options? OK, so you could decrypt it. So decrypting is just the opposite of encrypting. The problem with decrypting it is that if you're going to decrypt something like this on an automated fashion, well, that means that the web server or Harvard server itself needs to know how to decrypt it. And generally, encryption works by having some secret password or special key that only the website's owner knows. So if you wanted the website, like Google or Facebook, to automatically decrypt this and then compare your password, well, the implication is that then the website's password or key with which to do that decryption has to be stored somewhere in the server. So this then implies that if some bad guy breaks into the server, not only can he or she steal the crazy looking stuff like this, which is mostly useless, but if they have access now to the server, they can steal also whatever trick you're using to decrypt these things, because that's got to be implemented in source code, right? Whether it's C or some other language. So it's really not helping you if you've actually encrypted these in that fashion. Yeah. Yeah, exactly. So that's a nice solution here. So if the server is only remembering the ciphertext, and actually let me tweak my wording now. Though it's very similar in spirit to encryption, a better word for this would be a hash value, H-A-S-H. And a hash value is generally the result of encrypting something and essentially throwing away the key, though the mathematics are a little different than that. In other words, when you take a hash of some input, the result is some hash value, and statistically it should be impossible to reverse that. So it's one-way encryption, if you will. So that's OK, though, because if Facebook and Google are storing this as the king's password, well, that's fine, because the next time the king logs into this website, he types in his username, he types in 12345, hits enter, but then all the website has to do is take another hash of that input that is run 1, 2, 3, 4, 5 through the same algorithm, the same mathematical formulas. And if the output of that process matches the output of the original process, well, then you can assume that, OK, he must have typed in the exact same thing. So this is why IT people can't tell you your password, but you can continue logging in. They can't tell you it because this encryption is one way. It's taking the so-called hash of the original input. And this is for security purposes, because, again, it means if some bad guy steals all of this from your server, physically steals your server, breaks in over the internet, takes your whole database, they might have your usernames and your users' email addresses, which is perhaps bad for privacy. But at least they don't know your users' passwords because those are at least encrypted. And these days, if you read in the mass media or see on CNN some story about some website being hacked, the likes of Sony or the like, where their users' databases are stolen and you suddenly have to change your password, that is often because these companies, amazingly, aren't even doing something simple like this. There are numerous cases of companies, actual legit companies, storing users' passwords in the clear, just as 1, 2, 3, 4, 5, or whatever it is they typed in, and then you're screwed if that database is actually compromised. So towards semester's end, when we introduce web programming and MySQL and databases, we'll talk about these kinds of issues because it's actually, amazingly, relatively easy to protect yourself against this. So that's our segue today into security, and now back to C. So with problem set 1, if still tackling it, know that office hours are both tonight, and if you decide to cash in a late day, they'll be tomorrow as well in Lowell. Know that if you've been attending office hours and have had issues with wireless and whatnot, know that Harvard is actually installing more access points in all of these house dining halls for us over the next week or so that we'll have more capacity for everyone, as well as more cookies and the like. Also, if you have any remaining questions with the appliance, there's definitely been some FAQs about like cursors kind of spinning or windows not quite working. Realize we have solutions to all of these problems, so do reach out to us via help.cs50.net, catch me right after lecture, or email me directly in the worst case if you're really pushing up against the deadline. And then lastly, with the appliance, too, the only real challenging issues with the appliance is if you have an older computer, 3, 4, 5, 6 years old, or a fancy netbook that's by design very limited in RAM and CPU cycles. But we have a new solution for that, too, for the next problem set and beyond, where you'll be able to connect to our servers using a very minimalist program on your computer, not necessarily the appliance. So we'll announce that once details are available. So we should have solutions for all. So here we are, this little song last time, which is kind of itself a little tedious to both recite and also implement. But once you actually have the notion of, say, a loop, which we did, you were able to implement this with, as we saw, like a for loop. So let me go back into this week's source code. This was a file called beer1.c. So following along at home, this is in source directory for lecture 2. And if I go into here, beer1. So what do we now... How did we go about implementing this? Well, we have int main void, that's old hat. At the very top here, how many bottles of beer will there be? And then get int, so that just gets a number from the user. Then recall we had a bit of error checking. Just make sure the user's not messing with us. And in this case, we don't repeatedly reprompt them for a number. We just say, let's just yell at them, sorry, that makes no sense, and return 1. And return 1, again, is the notion like of an error code, an exit code. And then lastly, the actual implementation of this song simply happen down here. Sing the annoying song. So for int I gets n, so if the user types in 99, start counting at 99. On each iteration, subtract 1 from I, and that's what I minus minus denotes, the opposite of I plus plus. And then do this so long as I is greater than 0. And on each iteration of this loop, print this 4-line stanza. And the only thing that's kind of interesting here is this. 1, we have a placeholder for the integer, d, and we're plugging in I, as you can see over here. We have another placeholder that's identical. It's just the English words have changed. This is completely uninteresting because it's just a string, constant string that gets spit out every time. And the interesting aspect here is just this, because the song, again, is 99 bottles of beer on the wall, 99 bottles of beer, take one down, pass it around, 98 bottles of beer on the wall. So we need to somehow dynamically insert I minus 1, but we can do that very simply, arithmetically here. So I minus 1. So the only worry here you might have or should have is, all right, what's going to happen at the corner cases? A recurring theme in programming is you can get 98 cases perfectly right with your code, but that doesn't really matter at the end of the day if you screw up the first case or the last case. And by name, those are typically called corner cases. And so as you start writing your own programs and you start testing your programs by typing in values, well, a program like this, if you type in 5 or 6 or 7 or 97, odds are you're going to get the same fundamental behavior. But things get interesting if you choose those corner cases. Type in 1, type in 0, type in -1, type in 100, type in something distinct conceptually, something that's close to any boundaries you've defined to actually see whether or not something breaks. So in this version here, is there any risk of my printing out -1 bottles of beer on the wall? Will this ever print out -1 bottles of beer on the wall in that last line of printf? OK, so no, it won't. And why? What's the simple protection I've put in place? Yeah, so I has to be greater than 0 according to this, right? So as soon as I is not greater than 0, it is 0, this loop's going to stop executing, which means the value of I itself will never be 0 inside of this loop. The very last iteration will have a value of I equals 1, and so that's safe, because we'll say 1 bottle of beer, 1 bottle of beer, ... 0 bottles of beer on the wall, and we'll stop. But of course, if we had done something like this, so I'll go ahead and change this to greater than or equals. I'll save the file. Let me go down to my terminal window here into the source directory, and I'll type make beer1. And now I'm going to go ahead and run beer1 with, let's say, the value 99. Enter. Well, dramatic effect if we now scroll up to see what's actually there. There we go. There's the bug. So now we've introduced the bug, but we had it right the first time. So again, recurring theme, especially before submitting your pset, test these kinds of cases because the TFs are going to be looking for exactly these kinds of things. We're not going to test your program with 3 and 4 and 5 and 6 because most likely those are all functionally equivalent. It's the interesting, the negative numbers, the 0 numbers, the huge numbers that might ultimately be of particular opportunity for your code to break. Questions of any sort? Yeah.
How exactly do you implement the return 1?
How do you implement the return 1? Implement it in what sense?
Like, how do you use it to, like, jump back and get int?
Good question. So how do you use return 1 to get another int from the user? In short, you don't. So this was a deliberate design decision in this program that I'm not going to use a while loop or a for loop or a do while loop to ask the user again and again. If they don't give me what I ask for, which is a non-zero number of bottles, then I'm just going to quit immediately because it's not a fun song to sing. But we could have done this with a do while loop like in the P sets. Yeah? So how do you use this number return 1? So short answer, we're not going to yet. But starting next week, we're going to introduce something called a debugger, which is a separate tool from the compiler that actually lets you figure out what's going on inside of the computer and even lets you step through your code line by line by line. And for that tool and others, the return code is going to be useful. For now, it's the sort of thing, just take it on faith because it will soon become useful. So we now have beer 2. So we want to do something a little better here and introduce kind of a big topic that, frankly, you might see in a textbook, but no one ever really says it in person, which is that of hierarchical decomposition. So what does this actually mean, and who cares? So let me scroll down now to actually let me go with, let's go with beer 4.c. Yeah, this is the one I want. OK, so in programming, you'll often find yourself doing something a little repeatedly. Like if you yourself have been writing programs where you're kind of stealing code you wrote a few minutes ago on some other line and pasting it, that's probably going to be an opportunity for hierarchical decomposition, which just means write your own function. So thus far, we've been using main, which we have to write a program from the get-go. You've been using printf, which someone else wrote. You've been using getInt, which someone else wrote. So you haven't really, most likely, written your own function. And yet this is actually relatively easy. And it's not even new syntax. We just kind of mimic the same syntax we've seen with getInt and printf and main. So let's take a look at this version here. So if I zoom in here, notice at the very top of this file, I have, again, the same code at the top. How many bottles of beer will there be? I get an int from the user. I quit immediately by returning 1 if they don't cooperate. And then I have this two-liner, which is kind of interesting for a couple of reasons. So one, I have a while loop now. Why? It's just a little different from a for loop. I decided to do this aesthetically. But what's interesting, too, is I've got n minus minus. We'll come back to that. But more interestingly, all of a sudden, there's a chorus function that apparently I could have been using all this time to print out the chorus, that 4-line stanza, of this song. It's as though I've now outsourced to a little black box called chorus that itself is a function that someone else wrote, and that function's purpose in life is to sing this song for me. So I don't have to write these lines myself. Now, in reality, someone did have to write those lines, and in reality, it was me. And if you scroll down to the bottom of this file now, notice the following. So this is familiar syntax, even though we've not used this too many times thus far. The thing with the stars, that's just a comment. /*, then some stuff, then */. That's a multi-line comment, and that's just my note to myself, sings about specified number of bottles. Then below that, I have something that's similar syntactically, but still a bit new conceptually. I've got void, and then the word chorus, and then int b. And then inside of this, I've got a couple of new features. I have this new syntax, which we'll come to in a moment. So let's ignore anything we don't quite understand yet and focus only on this. Well, this is kind of interesting. Sing verses. So what am I doing that's different here? So I still have my %d, but what format code is now obviously new? So %s. So I'm actually fixing a couple of problems now and refining this code with a more sophisticated implementation. %d is still going to be the value of the number of bottles of beer. %s is going to be which of two words, even if you just take a guess. It's going to be bottle or bottles. So I'm fixing that grammar problem that I admitted to on Monday. So we'll come back to how that's working in just a moment. But B, what happened to I? Well, this is the fundamentally interesting aspect of actually writing your own functions. Notice that at the top of this function, I've specified what kind of input this function called chorus takes. And it's pretty obvious that it takes an int. And just because I'm going to be talking about bottles, I decided that B is a reasonable name for the variable to give to the input to this function. Now, notice how I'm using chorus. If I go up here, and actually let me simplify this just for a moment. I'm going to change this code just for the moment to I minus minus and then this close brace here. So notice on every iteration of this while loop, if I start by typing in 99 for n, what value apparently gets passed inside of parentheses to this function called chorus? This is 99, right? Whatever value's in n is what gets handed to chorus as an input. All right, so now let me scroll down to the bottom here. Well, just because chorus takes an int doesn't mean it has to take an int whose name is identical to what the original value was. I can name it anything I want, and I decided stylistically B makes sense because I'm talking about bottles. So what's going to happen then is when I call the chorus function up in main by just writing chorus, open parenthesis, n, close parenthesis, semicolon, what's going to happen is that chorus is going to get executed and be handed as input that number, 99, and it's going to get its own copy of 99, its own 32 bits, its own 4 bytes somewhere in RAM, and they're just going to be called B in the context of this function. Now, what am I doing with B? Well, let's scroll down to the printfs. Well, I'm apparently plugging in for %d, the value B. I'm plugging in for the value %d, the value B again. And then in the very last line, I'm plugging in for %d, B minus 1. So functionally, this is equivalent. All I've done is kind of outsourced now the singing of this song to someone other than main, and that someone is a new function called chorus. So now what about S2 and S1? Well, let me rewrite something quickly as this. If B equals 1, then I'm going to do this. String 1, S2. I'm going to say S1 gets bottle, else S1 gets bottles. And then I'm going to do a little quick copy paste here. And actually, let me clean this up. I'll do this on the fly. S2. And I'm going to do S1 up here. And I'm going to say if bottle equals 2, then I'm going to say S2 gets bottle, bottles. All right, so what is going on here? So first, let's ignore the goal and focus only on the syntax. Well, what does it mean if I say string S1 in a program? Just translate that to English. OK, not quite initialize, but declare a variable of type string and call it S1. This is identical conceptually to doing something like int n, semicolon. That means declare an integer, call it n, and that's it, because there's no equal sign. Don't do anything else with it yet. Now, a string, recall, is just a word, a phrase, a sentence, a paragraph. It's some number of characters. So string S1 means, OK, prepare to get me a string. And that string is going to be called S1. So what am I doing here? Well, if the number of bottles passed in equals 1, I want this string to represent bottle in the singular. Else, if B is anything else, 2, 3, 4, 5, whatever, then I want it to be bottles. So it seems like now I'm using just a branching condition to fix some grammar. And then I actually have S2 down here, but we'll see why in just a moment. So let me scroll down here and see what I'm doing. So printf %d. So if I type in 99, that goes there. If I type in 99, what's going to go here for %s if what I'm putting in there is S1? Bottles, right? So again, I'm just creating a variable on the fly here, string S1. And if B equals 1, make S1 be bottle in the singular. Else, make S1 be bottles in the plural. And so that's what gets plugged in there. Now, why S2? I'm going to wave my hand at this detail just for now. But it's simply because in the very last line of this song again, I might need to change the pluralization. Right? It might go from bottle to bottles, because it might be 1 bottle to 0 bottles, or it might be 2 bottles to 1 bottle. And so you need to have 2 different words. One might be singular, one might be plural, or vice versa, or they might both be plural. So that's simply why I have S1 and S2. Now, in terms of conditions, like we've done this before, right? If, this, else, that. And just so you've seen new syntax, it turns out that syntactically, these 2 lines at the very top are what we would call a very elegant one-line implementation of that same idea. By no means strictly required. Doing it the way I did here with the indentation and whatnot is perfectly fine. But let's just see what this is. This is the only funky line of code we're going to see for a while that has multiple pieces of punctuation in the middle of it. So what's going on here? Well, let's do the first part on the left. String S1 means give me a string, call it S1. That's it. The equal sign means put some value in there. So the last question to ask ourselves is, what value do you want to put there? Well, it turns out that this expression right here is identical to this It's just a slightly more succinct, dare say, prettier way of expressing that same idea. What this means is that if b equals 1, the word after the question mark is going to get plopped into S1. Else, so this colon represents else now, else bottles in the plural is going to get plopped into S1. So in other words, it collapses all 5 of these lines into one line that once you know the syntax, it's just a little easier to swallow, just a little easier to read. But let me point out one thing. I intentionally did this, string S1. Why, if you think back to Monday, did I not do this? It's only if I declare a variable, in this case a string, inside of a condition, that's pretty much equivalent, recall, to writing this, even though the curly braces are not necessary if it's just one line. But conceptually, it's equivalent to this. And what was the rule of thumb we discussed on Monday when it comes to variables? Scope. They're only in scope. They only exist inside of the confines of the most recent curly braces, even if those curly braces have been omitted just because it's one line of code for convenience. Those variables only exist inside of those curly braces, which means I'm kind of out of luck if I want to use S1 down here. And so the solution is simply make sure that the strings are declared outside of those conditions. So this, again, is a question of scope. So in short, we've solved a few problems here all at once. So on the one hand, with chorus, we declared our own function. It takes input. And now I don't have to clutter up my main function. If I have this well-defined task, sing the chorus of a song, that's a candidate for hierarchical decomposition. It just means factor it out. Create a little black box, give it a user-friendly name like chorus, define it as taking some input like an integer, call it whatever you want, b, and then it does something. And the only last question to ask about the syntax here is, what does it mean if chorus is prefixed with this word void? So not input. So it does take input because the input is always defined between the parentheses. So what's the opposite of input? So output. So this means chorus does not have any output. Now, this feels like a bit of a lie, because clearly this song is going to have some kind of output. What's it going to do? Well, it's going to print a whole bunch of stuff to the screen based on these printf lines. But this is a different type of output. Recall that you can print something to the screen, but you can also hand the user back a value. For instance, what's a function you've been using for a week or more now that returns some value? So getInt, right? GetInt, getString, getDouble. In those cases, the function getInt, it doesn't just print it out on the screen and leave it for you, the human, to figure out what it was. It returns it, so to speak, so that you can put it to the right of an equal sign so that you can assign its return value to some variable. Well, same idea here. Chorus, though, his only purpose in life is to have these aesthetic side effects of printing something to the screen. It doesn't actually hand the user back any value, any sentence, any string whatsoever. It just prints, and so its return type is void. And we'll see this again and again in more clarity. Yeah? Oh, so there is. We just scrolled beyond it. So if I scroll back up, recall that we began the story with main just as usual. Yeah?
If you declare a variable in main, will it still be declared in another function of the main?
Really good question. If you declare a variable in main, will it be accessible to another function like chorus? What do you think? So no, and again, you can fall back on the same rule of thumb. Variables only exist within the confines of the curly braces. So main has its own curly braces at the very start and the very end. So any variables in there are not, in fact, accessible by a function like chorus. And let me point out one other detail here before we can put to rest this singing song example. There's one piece of new stuff at the top of this file. So besides all of the comments up at the top of the file, besides my use of include cs50.h and standard.io.h, there's this thing, whose word is going to be called generally a function prototype. Well, what does this mean? So C is kind of stupid, right? It's an older language. The compilers for it are fairly, even though they've been updated over the years, they were very simplistic in terms of their design early on. And what does that mean? It means that the compiler, if you don't tell it in advance that a function exists, like chorus, and it encounters that word somewhere in the program before it's actually seen your implementation of that function, it's going to yell at you. it's going to trigger some kind of error. In other words, let me do this. I'm going to undo all of the changes I've done in this example, just so we know I didn't screw it up and it's back in its pristine form. And we'll come back another time to this syntax of doing the minus minus inside of the parentheses there. I'm going to go up to the top here. I'm going to expand my terminal window. And I'm going to go ahead and compile this thing, which again was beer 4. So make beer 4. I'm going to go ahead and run beer 4. And I'll type in, just 2 bottles to keep it short and simple. That seems to work. No weird side effects. So now let me break it. Let me accidentally delete this thing that we're calling a function prototype and just start typing main. And now notice if I scroll down further, main's there and chorus is still there. So in theory, I have all the building blocks I need. I've dragged all of my puzzle pieces to the stage. But again, C is not quite as smart as Scratch. C cares about the order in which you do things. So if I now recompile this thing with make beer 4, enter, a whole lot of stuff just broke. And this is the most telling line. And you might have seen this yourself over time. Implicit declaration of function, in this case chorus. Has anyone seen a similarly sounding message? Do you remember what the solution was the past week? Include the header file, right? If you've ever seen this message thus far, or you see this message in the future, implicit declaration of function just means you used a function, in this case chorus, but you didn't tell the compiler what it looks like, what's its return value, so to speak, and what's its input, what's its output and what's its input. And you kind of did, but you told the compiler it too late. You put your function all the way at the bottom of the file. So as soon as the compiler started reading your program top to bottom, left to right, it encountered this special new word, chorus, but you've never told it that there's a chorus function in existence before, so it throws this error. So just think intuitively, what's the quickest fix for this, perhaps? And the answer is not function prototype. Yeah? That sounds perfectly reasonable, right? So if the problem is I'm declaring chorus too late, I'm teaching the compiler about it too late because I'm using it in main, all right, well, let's just relocate it to the top of my file. So now chorus is at the top, main is at the bottom. Let me go ahead and zoom in now, and let's redo this. Make beer 4. Well, that actually did fix it. So that is indeed a very reasonable solution, but it's probably not the best because you can definitely, once your programs get more complex, you can definitely come up with scenarios where X has to call Y, but Y might call X. So you might get into these possibly these circular relationships where it's just impossible to put one above the other logically. And also, it's kind of nice as a matter of good style to just always put main at the very top of your program, because if you open a program that you wrote or someone else wrote for the very first time, you don't care about a function called chorus or anything else. You want to see what does this program do, and the answer to that is almost always going to lie in main. So ideally, we want to leave chorus where it was, below main, but it turns out the simple solution then is just to tell the compiler about this function before you actually implement it, and you just can do this with a one-liner. You specify what's its output, in this case void, what's its name, chorus, what's its input, int b. So in other words, you literally copy and paste the first line or two of your function and just put a semicolon at the end. You don't do open curly brace. You don't start writing your function. You just do this one-liner. And notice that is now identical to what's down here. Now, why this? This is just a matter of convention. It is perfectly legitimate to write your functions all on one line like this. But if you look back at the CS50 style guide, you'll see that we discuss why this is actually useful. Long story short, if you're using a text editor or like some kind of programming tool and you want to search where in your file you've actually implemented a function like chorus, there are usually little tricks in the find dialog to say start searching at the front of a line, the start of a line. So the fact that if you adopt this convention of putting the function name all the way to the left, it just means you can find it more easily when your files get big. But it's just convenience, nothing more than that. All right, so we'll come back to some of these syntactic features. But any questions on the concept of writing your own function and this notion of declaring it with this so-called prototype? Yeah? Good question. Why do you have to tell the compiler that it does or doesn't have an output? Can't you infer that from the code? You could infer it some of the time, but the problem is that if you just analyze a function that you've written, you could have an if condition, an else if, and it could actually return different things, maybe not even at all. And so the idea of proactively telling the compiler, this will no matter what return this data type, is a commitment you then make to adhering to certain conventions. So in short, it improves the probability of correctness, among other things. Any other questions? All right, so let's try to generalize this a little bit. So we just wrote a function. Functions have return values. Return values is just the buzzword for output. But we can run into problems with this, again, related to scope. Let's actually see a more concrete example where scope kind of breaks things for us with regard to these things called local variables. So this is a buggy program. This is buggy 3, and this is among the source code here. In lectures 2 source. If I open up buggy 3, we'll see an attempt to actually swap two variables. So let's ignore the top of the file. Let's just look at main, as is generally most useful. It looks like main declares an int called x, assigns it 1. Another int called y, assigns it 2. And then it prints out their values. It then says swapping, ... Then it calls a function called swap, who takes 2 arguments. So it's a little different syntactically, but you just separate the arguments with commas. Then it claims on the screen to say swapped, ! And then it reprints x and y. So this program's pretty simple, at least in terms of what we've learned thus far. The only new thing is this use of apparently a function called swap, which is not built in. I wrote it elsewhere in the program. So let's see if it works. It's not going to. So let's go into lectures to source. I'm going to go ahead and compile now, make buggy 3, enter. So compile's OK, so that's promising. Now buggy 3, enter. X is 1, y is 2. Swapping, swapped. X is 1, y is 2. Feels like this is definitely broken. So let's see. Maybe I did something stupid like I left out the prototype. Well, no. So that's there. I did include the prototype. And I should know that I did this correctly because GCC did not yell at me with implicit declaration of functions. So syntactically, this program's right. Apparently, swap returns nothing. But it takes an int, takes another int, and calls them a and b respectively. So let's now scroll down and see how I implemented this. Well, it's apparently just 3 lines of code. So swap has no output. It takes 2 inputs, a and b. Each of them is an int. And now conceptually, does this sound correct? So it actually is. So here's one gotcha first. If you've got a value, let's call it a, and another value, call it b, how do you swap them? Well, if you think about it, you sort of visually, you do this, right? But you can't quite do that in a computer, because if you say a gets b and then b gets a, well, what value is in both a and b? So it's b, right? Order of operations, if on the first line you put the value of b in a, and then you put the value of a in b, well, that means that b's value, whatever it is now in both of those variables. So what's the solution? Well, you introduce, we'll call a temporary variable. Now, usually TMP would be a silly name for a variable, but if it is a temporary variable, it's quite reasonable here. So the solution is to remember what a is by storing its value in an int, then updating the value of a and putting in it the value of b. And now at this point in the story, what value is in a? Well, the value of b. What value is in temp? The original value of a. And so now we can put inside of b temp, which is equivalent to a. So we just need a third line of code. Now, as an aside, especially for those of you interested in hacker editions, there actually is a way in C code to do this, where you swap 2 variables simultaneously without using any temporary storage space. It's kind of a nice magician's trick, but more on that perhaps next week. But for now, this code feels correct, right? I've got a and b. I put a in a temporary variable. I change b. I put b in a, and then I put this guy here. Right, so that logically feels correct. And in fact, at the very last line here, where my cursor currently is, a and b have, yes, been swapped. But we just saw when I run this program that x and y are not swapped, even though I'm passing x and y to this function. So where do things break? Someone, yeah, in back. Oh, sure, you.
Well, it's not assigning it back outside the function.
OK. So it's not assigning the answers back out of the function somehow. OK, so that's true. And what other point can be made too? Here, yeah.
The values of x and y that it's taking from the main function get messed up when they're passing on to the swap function?
OK, so maybe the values x and y are getting messed up in some way when being passed in. So messed up isn't quite what I'd say, but there is there's a verb here that would apply. They're being copied into the swap function. So recall earlier, and I said it briefly in our previous beer example, that when you call a function and you just specify the input with a variable name, you get the value, but you get a copy of that value. So at this moment in time, when this program is executing, there are now 4 variables, actually 5 variables in existence in this program right now. There's x and y, and those live inside of main. There's also a and b, and also temp, TMP, so 5 separate integers. That's 5 separate chunks of 32 bits somewhere in the computer's memory. And inside of x is the number 1, apparently, if you think back to how we started. So inside of x is the number 1. Inside of what other variable is also apparently the number 1 initially, before swap executes. So also the number 1. Y has the value 2. As soon as we call swap, B has the value 2. But then when you finish executing swap, before it actually finishes, so if we get conceptually right to where my cursor is here before it's all done, x is 1, y is 2, a is 2, and b is 1. The problem is that the goal is to swap x and y, and all we've done is swap a and b. So it seems to be a fundamental problem that when you pass inputs to a function, you're actually passing copies of them in. And the buzzword here is you're passing them by value. Now, those of you with prior programming backgrounds know that in Java, you actually don't run into this, at least if you're using objects. And we can fix this in C. Fast forwarding to a couple weeks from now, we'll introduce the notion of pointers and low-level memory addresses. But for now, let's just assume we've run up against a wall. Right now, when you have what are called local variables, which x and y are, anytime you have a variable inside of a function, it's called a local variable. It's kind of for self-explanatory reasons. It's local to that function. That function cannot, that variable cannot be accessed in some other function, because a and b, meanwhile, we keep calling them arguments or parameters, but they're also just local variables. They exist only inside of swap. So at this point, then, there's 2 variables in main, there's 3 in swap, and those guys, even though they might share some values, they're copies of those values. And we can actually see this as follows. So this is a little picture that we might paint of a computer's memory. So if you think about now your own computer, you've got like a gigabyte of RAM, 2 gigabytes, 4 gigabytes, something like that. Let's just assume that your RAM looks like a rectangle. And RAM is, again, 1 gigabyte, 2, 4 gigabytes. And bytes is the key word there. If you have a total number of something, you can number those things. So this thing at the bottom left, this might be byte number 0. If I move my hand over a little, that's byte 1, byte 2, byte 3, byte 4. Then I go up to the next row, that's byte 5, 6, 7, and 8. In short, we could assign like 1 billion unique numbers to every little square portion of this picture, if this whole rectangle represents my computer's memory. So what happens when you actually run a program? Well, when you run a program, what function gets executed by default? It's just main. Right? So main gets executed by default. Main might have some local variables. Where do they end up? They end up at the very beginning of your computer's memory, let's say. This is a little bit of a simplification, but they'll end up at the bottom left-hand corner there, inside of the rows labeled main. Now, main can take arguments. Thus far, we've been writing int main void. So right now, there actually are no inputs to main, but we'll get there. Main's locals means all of main's local variables might end up there. But what if main calls a function like printf or getInt, or in this case, swap? Where does it end up? Well, where does swap and all of its local variables end up? 1 layer higher, literally in RAM. If something starts here, the next function ends up here. The next function's variables end up here, and here, and here, and here, and here. So where we say foo, and foo, incidentally, is like a mathematician might say XYZ. Computer scientists say foo bar baz, quux, and then there's some other crazy words. Just when you need a verbal placeholder. Foo's local variables end up on top of main's. And guess what? If foo calls its own function, where does it end up in memory? Here, and here, and here. So again, one of today's and next week's themes are security. Turns out that this is actually a brilliant way of hacking a computer. If you have the ability to call a function that calls a function, that calls a function, that calls a function. If you do this enough times, you can actually start to change the contents of a computer's memory, potentially in dangerous places. And so if you've ever heard of a word like a buffer overflow exploit, or more generally, a website being hacked, to this day, it is still incredibly common to hack into computers by passing them bigger strings or bigger numbers than they were expecting. And what happens is those strings or numbers start filling up space in your computer's RAM at the bottom left, but it gets so big that it overwrites something important. And for today's purposes, that's bad, because if you overwrite something important, you can actually trick the computer into executing almost anything you want. But it derives from this problem here. So just to hammer this home, who cares about these rectangles in this depiction of memory? Pictorially now, if you have x and y and they live inside of main, just graphically, they are not accessible to foo, and vice versa, because they're ending up in different locations in memory. So let's actually go back here and try fixing this. So I could fix this by introducing not a local variable, but a global variable. So let's scroll down here. The only thing different now in this version of swap is that I'm actually going to, sorry, not of swap, in this program, I'm going to try to solve this problem in this way. So let's scroll down here, and let's simplify this. Rather than involve two variables, x and y and swap, let's simplify. Let's instead change the story to a function called increment. And increment's purpose in life is just to increment a variable. So let me change this real fast. Let me break this, and then we'll fix this. So look at main here. I've got an int x gets 1. I then claim initialized, because I've initialized it to 1. X is now 1. Incrementing, ... I call the increment function, not even passing in a value here. Incremented, and then I claim it's some new value. So if I look now at increment and I try to do this, will this work or not work? So no, and what's the short answer? I'm trying to do x++ inside of increment, but so it's a void function, which means it has no output. It doesn't return anything. But more worrisomely, what else is also buggy here? Yeah? Exactly. This x was not declared inside of increment. It was declared inside of main, which means you don't have the right to actually do ++ here, and you can't even compile this. If we run make on this, it will just yell at us that x is not initialized, because it's not in scope. So how can we fix this? Well, you know what? Rather than make x local, let me try another little trick and scroll up here, and let me actually declare my int outside of this whole program. And if I declare the int x at the very top here, now there actually aren't curly braces anymore, because I'm outside the huge main file. But is x, do you think, in scope or not in scope now with regard to the rest of this file and all of its functions? So it actually is in scope. So just as before, where the quick fix was just copy and paste our whole function, put it at the very top, here too, we can kind of fix this by just putting our variables at the very top of our program. And now both main and increment and any other function here can execute them. All right, is this a good thing, bad thing? In this case, it actually solves the problem very reasonably, and it gets the job done. But what's maybe a downside of these things now called global variables? Global in the sense that they're not inside of functions, they're inside of files. Someone, how about over here? Any? All right, over here. There we go.
So for example, if you globalize x over there and there's another function with a very long program and you accidentally use the same variable.
Good. Yeah, so if you start thinking ahead, and granted this is a little hard to do when we're just implementing pennies thus far right now, and similarly short programs, realize that this is also a solution that doesn't really scale very well. Before long, we'll be writing more sophisticated programs that have more variables than just one. And so again, as a matter of good design, if you just start plopping all of your variables at the top of your file as globals, you totally defeat the purpose of trying to declare your variables as close as possible to where you actually use them, which lends themselves to readability repeatability, and it's just easier to understand what your program's doing if you do everything really only when you want to use something. If you're just littering the top of your file with these global variables, long story short, this does not scale well. And in fact, once you start using other people's code, libraries or APIs, like I referred to a week or so ago, things like even CS50's data APIs for course catalog data and shuttle data and dining hall data and the like, once you start using code that other people have written, my God, what if you use a variable called x and that other person uses a variable called x, right? What if the person who implemented printf in a file called standardio.h and another file, standardio.c, what if he or she also decided that he or she needed a variable called x, so he or she put x at the top of their file? Now you have collisions. And this suggests that now you can't even use the variable x if you want to use printf. So again, long story short, putting stuff at the very top of your file in terms of variables tends not to be the right solution. So they exist, and we'll see cases where global variables are compelling, but thus far, this is not, in fact, the right solution. Well, let's see if we can't now completely abuse some of these ideas and see what bad things can happen. So I'm going to go ahead and save this as, let's say, bad.c. And I'm going to go ahead and zoom in here. And I'm going to do something like include, let's say, standardio.h. And I'm going to have int main void. And then here I'm going to do something. I don't know what yet. I'm going to then have a function called void bad. Can be the same thing as the file. Is it going to take any inputs? No, not even going to take any inputs. So I'll say void. But I could have it take input. And now here I'm going to say printf. Oh, you know what? I will have it take input. Let's have it take an integer n. And what I'm going to have it print out is that value of n followed by a new line character with %d. So all this function does, and it doesn't seem all that bad thus far, all it does is it prints out the value of its argument. So how do I call this? Well, let's do int n gets, let's say, 0. Let's call bad of n. And that's it. So what will this program print when I run it? So I think it will just print 0, right? Quick, super quick sanity check. So if I do make bad, oh my gosh, so many mistakes. All right, good. So when you see lots of mistakes, just listen to everyone yelling at you and fix it this way. So with double quotes, hopefully that's fixed now. OK, nope, what'd I do wrong still? Yeah, exactly. I simply haven't declared bad. So fix 1 could be move it to the top of the file. But again, better practice is leave main at the top. And instead, what do I type at the very top of the file? Void bad, the same thing, but semicolon. All right, so now let's see if I fix this. Let me go back to the bottom. I'll zoom in at the bottom. Let me rerun make bad. OK, that's good. Bad. OK, so we're on our way. Not an interesting program. But now suppose you do this. Interesting thing here is that main is calling bad, but that's it. I could really create an interesting quandary here and perhaps send a message along the lines of don't do this if I did something like this. What if I did bad in here and I passed in first n gets n plus 1. Or let me keep it simple, n++, and pass in bad here. So what's going to happen? This should hopefully start messing with your mind. So main gets called. We initialize n to 0. We then pass that into bad. Now, quick sanity check. Is this a coincidence or necessary that I also called the input to bad n? So it's not necessary. This is actually just a coincidence. Why? This is actually maybe confusing. So I'll change it. Let me change it to I, and I'll change this to I. And I'll change this to I, because again, I, or whatever I call it, is going to be a copy of n. But it doesn't matter if they're named the same, because they're in different scopes. So you can reuse names of variables if you want in this way. So OK, so main initializes n to 0, passes in 0 to bad. Bad takes as input that value 0, and it prints out 0. Then I gets incremented from 0 to 1. And then bad gets called with what input? 1. So what happens next? We don't go back to main yet. Instead, bad gets called again. So if you're kind of thinking through this linearly, we're chugging along here, 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 here. Then we do this again and call bad again. So at this point, bad takes as input 1, prints out 1, and then does what to I? ++, so it becomes 2. Then bad prints out 2, and then 3, and then 4, and why is this kind of a problem? All right, so it never stops, right? And you might have done this accidentally with infinite loops already, and that's kind of bad if you have an infinite loop that never stops because you messed up your condition. But now if you think about what's going on inside of the computer's memory, it's kind of worse when every time you call a function, it turns out it's using some amount of memory. In fact, it's using, let's say, a sliver's worth of RAM in your computer. But every time you call a function, it goes on top of the previous function that was called, on top, on top, on top. So even though bad is the same thing, every time you call it, you get a distinct sliver of memory again and again and again. And so if you kind of think through this, if you do this infinitely long, what's going to happen? Well, you're going to overflow your computer's RAM. And this is just the bottom of your RAM. If we actually redraw this and actually acknowledge that you only have a finite amount of memory, you've got 1 gigabyte or 2 gigabytes, you do not have an infinite amount of RAM, well, there's got to be something probably at the very top of that. And indeed there is. If you think again about your computer's memory as this big rectangle, the thing at the bottom now we'll call the stack. Every time you call a function, you just keep stacking more and more memory on top of the stack. But it turns out at the very top of your computer's memory, there's what's called the text segment. And text is just a fancy way of saying that's the zeros and ones that represent your actual compiled program. In order for them to run, when you double click them or type their command at the prompt, they get loaded into memory. So if nothing else, your own program is somewhere there in RAM. And if you keep calling bad, 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 what's going to happen? You're going to literally overwrite other stuff with the zeros and ones that represents bad's stack frame, its local variables. He only has one local variable, I, and that's 32 bits. So frankly, this is going to take a while to get all the way up to the very top if we're only doing it 32 bits at a time. But if we're doing it infinitely, we'll get there eventually. And you're going to start overwriting potentially important stuff. And this isn't quite how a bad guy would do it, but it's the same idea, whereby you can then change what code is inside of your own program and trick a program into executing something bad like disable the serial number prompt or disable the password prompt or give me administrator access. So I've compiled, let's recompile this now that I've introduced this infinite loop by way of calling bad, 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 and run this. And let's go ahead. Went a little long, but let's take our 2-minute break now, leave this up and running, and we'll come back and see if this is actually broken. Oh, OK, break's over. Now let's still take our 2-minute break, then we'll come back. So in short, a couple takeaways thus far. So we implemented the capability of implementing our own functions. And syntactically, it's really no different from using main, using getInt, and the like. But we did see one gotcha, whereby if you use a function you wrote, and that function's written at the bottom or just elsewhere in your file, you do have to declare it, so to speak, at the very top. And the jargon there is you give it a function prototype. You declare it at the very top of your file, ending it with a semicolon. So then we looked at, again, this issue of scope. And the issue of scope refers to where variables can be used and cannot be used. And if you declare a variable inside of a function, pass it to another function, that function gets a copy of it. And you can't access the other guy's copy back and forth. And that is because of this little picture that we started to draw here, where your memory is given, your program is given different slivers for every individual function. Now, if you take this to the extreme and call some function an infinite number of times, eventually you're going to hit some kind of ceiling. And that ceiling, among other things, has your own program in it, your own program's zeros and ones that were the result of GCC compiling them. And what eventually happens is usually something like this. Odds are this won't really happen to you this week unless you're doing the hacker edition of PSET 1, but this will happen to everyone in this room over the next couple of weeks. Segmentation fault simply refers to the fact that you started in some segment at the bottom of your memory, and you overstepped the bounds of someone else's segment, some other important chunk of memory. So this is actually a good thing in that the computer's trying to prevent bad things from happening. But as we'll see, we can actually, with finer grain control, take advantage of a computer's memory. And again, to be clear, the context here might be malicious behavior, not just compromising a server, but frankly, a common pastime on the internet is to create cracks for programs, whereby when you want to install Microsoft Word or Photoshop or something like that, you're usually prompted for your registration code or product code, something like that, that in theory only you have. Well, how are those things implemented? If you double click on Photoshop for the first time, there's probably just an if condition in there that says if not yet registered, show prompt, else show program. Right? So conceptually, it's probably as simple as that. So what do bad guys do? Well, they try to figure out where in the program, where among those zeros and ones, there is that condition to try to circumvent it or try to overwrite it with code of their own. So again, this all relates to the capability in most programs to take advantage of or even break their use of memory or even their use of disk space. And it's all because you can address every single byte by way of its number. Byte 0, byte 1, byte 4 billion if you have 4 gigabytes of RAM or 4 gigabytes of disk space. So let's now explode something we've been simplifying in the CS50 library. A string, again, is what in English? So it's text. It's a word. It's a sentence. Maybe it's a single character. It's 0 or more characters in a row. And this is actually the case in memory, too. If I wrote that program a week ago called Hello World, and I typed in HELLO and hit Enter, and that HELLO was stored inside of RAM, those characters would be stored back to back to back to back, one ASCII character, one byte, after the other. And in fact, what really happens inside of a computer program is if I type in HELLO, here's a formerly blank chunk of memory. So this is the first few bytes of, say, 4 gigabytes worth of memory. When I type in HELLO and store it in a string, what really happens is this, HELLO. And then the next word I type in, if it's hello world, might be WORLD. But this is a bit broken, and it's a bit of a lie, because you need some way of distinguishing boundaries between words. So what C actually does is, even though when you type words at your keyboard and they're stored in these variables called strings, even though it does store the word one character after the other, it also puts a special, let's call it sentinel value at the very end. And I'm going to denote this with \0. So we've seen \n, and the backslash almost always denotes something special. It's an escape character. \0 is the way of representing a byte whose 8 bits are all zeros. This is a special character. This is in contrast, just to be clear. If I wrote just 0, that's actually the ASCII character, the text that looks like the number we know as 0, but the letter 0, the ASCII character 0, is not 0000000 in terms of bits. So \0 means a byte's worth of all bits. A byte's worth of all zeros. And I need this one other place, \0, so that now if I have an exclamation point at the end of my sentence, I might have another exclamation point there. So if I typed in hello and hit Enter, this ends up in memory, followed by this \0. If I then on another line type in hello world, it ends up in memory in the same way. If I type them both together with just a spacebar character, you do not get a \0 after every word. You only get a \0 after every string. So the moment when you use the CS50 library and use getString and hit Enter, the \0 ends up at the very end of the string. You might still have spacebar characters in the middle there. So what's the application here? So it turns out that a string in C is just a new data structure called an array. And you might recall from the tail end of Scratch, or specifically the Fruitcraft RPG game, where the little guy walked around stage and he actually picked up like oranges and apples and pears, those kinds of things. He was putting them into a list, so to speak, and to use Scratch's terminology. Well, that's really just an array. An array is a data structure. It's like a special variable that doesn't just store one thing. It can store 2 things, or 3 things, or 4 things all together. This is great for strings because what's a string? It's 0 or 1 or 2 characters all together. So the way in which C implements strings is it takes a chunk of memory, puts the first character here, then here, then here, then here, and at the very end of the string it puts \0. And so what the implication here is that even if you have a string that's been passed in by the user at the keyboard, you can actually get at individual characters in it because they are all back to back to back in this way. So let me go ahead and open this program called argv1. And we can finally reveal what that special thing called argv has been that you might have seen in textbooks or any of the online references. So thus far, all of our programs have been declared with the very simple void. But the question was asked, I think, on Monday, what does it mean if you actually have something other than void inside of parentheses? What if you want a program to take command line arguments? Well, what's a command line argument? Well, most of the programs we've been using down here in the terminal window take command line arguments. There's a program called make, but anytime you type something like beer 4 at the prompt, you are passing to make a command line argument, which is similar in spirit to calling getString and asking the user for a string. But notice the one key conceptual difference. A command line argument is input, is a word that the user types before he or she actually runs the program. So it's passed to the program as at the so-called command line. So how does make, how does GCC, how do any of the programs we've been taking for granted in the appliance actually access those? Well, now we can change what main looks like. This is the other correct declaration of main. And it's a little scarier looking, but we'll tease this apart in just a second. Int is the same. Main is the same. What do you think argc and argv might represent? So arg denotes arguments. So just as another function like swap or increment or any of these functions we've been playing with today, or chorus, just as they can take arguments, it turns out main can as well. Thus far, none of the programs we've had to write take arguments at the command line. We hit enter, then we're prompted for a string via the use. We then prompt the user for a string. But if you actually want to take the argument at the very command line, you can declare main as this: int argc, which stands for argument count. And then you can declare this: char star argv, open bracket, close bracket. So this will make sense in just a moment. Let me actually simplify this for a moment and rewrite this as this, which is, again, sort of CS50 style. Not quite correct, so we'll fix it in a moment. This means that argc is a number, and it's argument count. How many words did the user type at the prompt? Argv is what's called argument vector, which is usually synonymous with array. So it's a list. It's a collection of words that the user typed. So when you type in multiple words at the prompt, where do they end up? They end up in a variable called argv. And the square brackets is just C's way of saying this is an array of arguments. That is, this is multiple words, multiple inputs, all inside of one variable, like a scratch list. I'm going to leave this as string for just a moment, and let's actually see what this program does. I'm going to go ahead and go down here, and I'm going to compile in lectures to source. I'm going to compile argv1, enter, and now notice unknown type string. How do I fix this? Yep, include cs50.h. So now let me go back to my prompt and rerun arg. OK, that's good. Now I'm going to run it, argv1 foo bar, enter. Interesting. It looks like this program simply does what? Prints out what you typed, but one word per line. And then it's got some, just for aesthetics, just some blank space at the top and blank space on the bottom. But it looks like it literally regurgitated what I wrote, Baz, or just like this, right? So it's just spitting out those words at the prompt. How did we get access to them? Well, it's actually pretty easy. So notice again that main is now being passed a special number, the number of words that were typed at the line, then a string, but not a string, an array of strings, as represented here. So this represents the number of the words that were typed at the screen, at this command line. So let's see what happens. I print \n. Why am I iterating from I equals 0 to argc? Conceptually, what does that mean? Just iterate over all the arguments. Iterate from 0 to whatever the number of total words there were that were typed. And now this is familiar. %s means put a string here. What string do you want to put here? Well, if argv is said to be an array or a vector of words that were typed, turns out that syntactically, you can get at the first word by typing on your keyboard argv of 0. That's the very first word that was typed. argv1 is the second. argv2 is the third. argv3, 4, 5, 6, and so forth. Those are each of the individual words numbered from 0 on up that you typed at the prompt. So if I want to generalize this, I just say I, and this means get me the ith word that was typed at the prompt and print it out. So now I can go ahead and print this as follows. If I go back again, and I go ahead and run this, and I say, yes, indeed, enter. It does exactly that. But notice, too, it's also including not just the words I type after the program's name, but also the program's name itself. So this actually means you have the ability to see what your own name is, which is sometimes useful. But let's take this one step further. Not to make this too complex, but let's take this one step further. Let me go ahead and open up version 2 of this file. It looks a little scarier. Let me go down to my prompt and run argv of argv2. argv2. I'll zoom in, enter. Compiles OK. argv2, enter. Interesting. Hi. So what's this one doing differently? Obviously. So now it's doing not one word per line, but one character per line. So this suggests that programmatically, I must have the way not only to iterate over each of the words that the user types, but also over each of the just the characters that they typed. And that's because, too, just as argv itself is an array of strings, well, guess what a string is? It's an array of characters. So we can apply this exact same logic. Let me zoom in now on this version 2. And again, at the top here, I have this. And I simplified this a moment ago. This is the first training wheel that will eventually take off. When we keep saying string in C programs, technically, it's really something called char star. And the star is just a little confusing for now. So we hide it under the guise of something called string. But know for now that these are synonymous. It's just we're currently in the habit of calling those things strings. But we will get rid of that convention in a week or two. So now let's look at what this program's doing. It's iterating from 0 to argc again. OK. It's now iterating from another variable, j equals 0. What do you think string length of argvi means? String length, strlang, is it's just another function. It's in a special library, and it just gets you the length of a string. So what does string length of argvi generally mean? Give me the length of the ith word that the user typed at the prompt. That's it. Give me the 0th word, the first word, the second word, the third word, and get its length. Now, as an aside, how do you figure out the length of a string? How did whoever implemented string length 40 years ago, how did they do it? You just start at the first start of the string and look for what? \0, and then you return the total number of characters you saw before the \0. So that's actually a pretty simple program, a function. But let's see what we're doing. There's one piece of aesthetic difference here. Notice that you can actually declare multiple variables at once inside of a for loop. You just put a comma there. So I'm declaring not only an int called j and setting it equal to 0. I'm also declaring another int called n and setting it equal to the length of the string. And then I'm iterating from j up to n. So from 0 up to the length, because I'm doing j++. So now notice, we can apply this same logic. So again, the syntax is new, but the idea we're just mimicking. If you can index into an array of words called argv with the square bracket notation, but the thing that's there is a string. And what's a string? It's just an array of characters. You can then use double bracket notation to say, give me the ith word and give me its jth character. And if you do that, this seems to empower us now to iterate over all of the lines and all of the words and all of the characters in a string one at a time, printing them out by way of the familiar printf, but this time %c, because it's a character, followed by \n. So in short, what is an array? It's just a contiguous block of memory inside of which are the same types of thing again and again and again, either a word, a word, a word, a word, or in this case, a character, a character, a character, a character. So who cares? Well, it turns out that back in the day, back in Caesar's day, literally, there was something known as the Caesar cipher. And the Caesar cipher is not unlike the grade school flashback I had the other day, whereby you might pass a note handwritten to a significant other in your 3rd grade class, but you want to encrypt it by actually rotating the characters in the message by one place. A becomes B, B becomes C, and so forth. And we teased earlier on Monday that you could do this now programmatically because a letter is just a number, like 65 is A and 97 is lowercase a. So you could actually convert letters to numbers, do some math, and then convert numbers back to letters. And you could do this now with the computer program. And indeed, according to legend, this is exactly how Caesar himself encrypted messages to his generals in the field, taking hopefully a secret number bigger than 1. He didn't just rotate letters in their alphabet by 1, but rather some bigger number or something similar. And so thus was born what's called the Caesar cipher, a rotational cipher whereby you rotate the letters in some word by some number of places. So in problem set 2 next week, you will see the same idea applied, where you'll have to implement your own forms of encryption, your own Caesar ciphers, and some other ciphers whereby you'll take input and have to produce output whose input might be 1, 2, 3, 4, 5, but the output should be something much harder to actually decode or decrypt. And the little teaser here, have about 1 minute left on the clock, is that all of this actually relates to a little thing you see on the screen here, Little Orphan Annie, which is stolen from a movie called, anyone know? A Christmas Story, where little Ralphie has been listening to the radio for ages, hearing secret messages from them, and he tries to decrypt them, and they finally send him Little Orphan Annie's secret decoder ring, which just allows you to rotate the ring and map A to B and B to C and so forth, but in some general way. And so this was Ralphie's and soon your discovery.
Secret Circle is entitled to all the honors and benefits occurring there, too.
Signed, Little Orphan Annie. Countersigned, Pierre Andre, in ink. Honors and benefits, already at the age of 9. Come on, let's get on with it. I don't need all that jazz about smugglers and pirates.
Listen tomorrow night for the concluding adventure of the Black Pirate Ship. Now it's time for Annie's secret message for you members of the Secret Circle. Remember, kids, only members of Annie's Secret Circle can decode Annie's secret message. Remember, Annie is depending on you. Set your pins to B2. Here is the message. 12, 11.
I am in my first secret meeting.
14, 11, 18, 16.
Oh, Pierre was in great voice tonight. I could tell that tonight's message was really important.
3, 25. That's a message from Annie herself. Remember, don't tell anyone.
90 seconds later, I'm in the only room in the house where a boy of 9 could sit in privacy and decode. Aha, B. I went to the next. E. The first word is B. S. It was coming easier now. U. 25. That's R.
I'll be right there, Ma! Gee whiz.
T. O. Be sure to. Be sure to what? What was Little Orphan Annie trying to say? Be sure to what?
Annie has got to go. Will you please come out?
All right, Ma. I'll be right out.
I was getting closer now. The tension was terrible. What was it? The fate of the planet may hang in the balance.
No, Annie's gotta go. I'll be right out. For crying out loud.
Gee, almost there. My fingers flew. My mind was a steel trap. Every pore vibrated. It was almost clear. Yes, yes, yes,
Be sure to drink your Ovaltine. Ovaltine? A crummy commercial? Son of a bitch.
And thus you have encryption. We'll see you next week.